Today is going to be an intro to factoring quadratics. What we're going to be doing over the next several videos is we're going to go over different topics that are going to cover some basic forms of factoring with an ideal focus of factoring quadratics. A couple different techniques. We're going to build this from the ground up. Now, the whole idea of what is factoring is the idea of we're going to be undoing the form of distribution. Now, we all recognize what distribution is when we see two binomials multiplied together. So if we were to see this, we would know that, hey, I would need to multiply everything outside this parenthesis. So that would be the 2 and the x times everything inside the parenthesis. So I would take my x and I would multiply it times both of my other terms. X times x would give us an x squared. X times -3 would give us a -3x. We know that also the 2 would be multiplied times both of these terms. So I'd say not only am I multiplying x, but I'm also multiplying 2. So 2 times x would give us a 2x. 2 times -3 would give us a -6. The next step that we would have to do is we would combine our like terms. We notice these middle two terms are both single x terms. We're going to combine a -3 and a +2 to give us a -x or a -1x. Then what we would do is we'd put -6. And so quite literally, this is the expression that we're going to be doing. So our first step is we would be distributing. We're going to distribute each term. Boom, to move to the next one. To move to the next one, we would combine and put an alpha numeric. Boom, and so we get to this point right here. Now the whole idea of factoring is to go from our answer, which is this part over here, somehow to get back to the original question. How do we undo this multiplication when it looks like that middle step has been combined? We're going to go over a couple different techniques to turn this into this form of expression to get it back even further to the original form. So one of the questions we do like to ask is, can you make any observations about this expression right here, specifically concerning these two parts? So concerning the -6 and concerning the -1. Relating it back to these two constants. If I have these two constants being a +2 and a -3, let's look at these two different ways. One way where I multiply them, I get my -6. Let's do this in red. If I multiply, I get my -6. Another way to look at them is if I have a +2 and a -3, and I just simply combine them, I get my -1. So I add them together. So we have two different ways to break this down. We're going to be specifically concerned with this -6 and this -1, and between those two values, we're going to find our 2's and our 3's. So a quick question that generally we like to start out with is, what factors of blank make a blank of blank? And this is one of my favorite sayings. What factors of C make a sum or difference of B? Okay? And when we're asking about the factors, the signs do not matter. We're just simply looking for, if we're concerned with factors of 6, I'm not concerned with positives or negatives in the first step. When we're looking for a sum or difference, the signs now all of a sudden do matter. And then for the sign of B, yes, B is an important sign. And we'll go over exactly what that's going to cover later on. So the 4 different types of factorings that we're going to be doing over the next several topics is going to be factoring by grouping, a standard quadratic where a is equal to 1, so when there's no leading coefficient, a standard quadratic when a is not equal to 1, and then any sort of special techniques. So this topic is we're going to be reviewing distribution. Now, distribution simply means that we're going to multiply each term outside the parentheses with each term inside. When we have multiple parentheses, we have to do this multiple times. So we've got a couple different methods we can do this. We notice we have two sets of parentheses, which means everything inside here, the 2x and the 4, gets multiplied by everything over here. So 4 gets paired up and 2x gets paired up. These are the three most common ways. Now, foiling specifically, if we're not going with standard distribution, means that we're going to multiply the first, the outer, the inner, and the last. So we're going to look at that as a form of distribution. So let's go ahead and rewrite this expression. So I'll have a 2x plus 4, 3x minus 7. And so what we're going to do is we're going to say first times first. So I'm going to draw a line that shows that. It's going to get me my 2x times my 3x, which is going to give me a 6x squared. Then we say outer, so we multiply the outside two terms. So 2x times negative 7 is going to give me a negative 14x. Inner is these middle two terms. The positive 4 and the 3x are going to give me a 12x. Last means the second term or the last term in each one of them. That's going to be a 4 times a negative 7, which is a negative 28. So once we've gotten that done, we can see the fact that we have, in fact, had our FOIL. We're going to combine our two terms right here in the middle because they both have a single x, and we're going to be left with a 6x squared minus 2x minus 28. Let me get that. So this is the standard method of distributing two binomials, is foiling. First, outer, inner, last. We notice it looks very much like the setup that we've done previously when it comes to distribution. Another very common method that's a little bit more visually appealing than FOIL, it lets us know what terms we're going to need to combine. This is specifically helpful if we start adding on more and more terms. So if I have a trinomial and a trinomial. So let's take a look. 2x plus 4. 3x minus 7. So what we've gone on right here is we're going to do the same process. We are going to distribute this 2x to both terms, times the 3x and times the 7. That gives us a 6x squared minus 14x. The only difference is that when we combine these two terms, and I say 4x times 3, that gives me a 12x. I'm going to scan through my previous answers and say, do I have a single x term? Yes. So I'm going to stack it. So 12x, right beneath it. The 4 times the negative 7 is going to be a negative 28. I don't already have a constant column, so I'm going to put it over there. What this allows me to do is this allows me to add up my different columns. I have no other x squared terms, so that'll leave me with a 6x squared. Negative 14 and positive 12, I know I need to combine these to get a negative 2x, and then minus 28. Boom, so we end up with that. We notice we end up with the same answer. Again, this is a little bit more visually appealing when it comes to which terms do we need to combine. That way you don't have to have a huge list of different numbers. The table method is slightly different. The table method says we set up this as a 2x and a 4, and we're going to make those rows in a table. So we have that. I have a table with 2 rows. And then I'm going to set these as the columns of my table. So a 3x and a minus 7. And all we're going to do is we're going to work our way across. So we're going to say row by column. So 2x times 3x gives me a 6x squared. And then I keep going. Row by column, negative 14x. Row by column, 12x. Row by column, negative 28. And then our answer, we're going to do we notice that our terms that we need to combine are in perfect diagonals. My 6x squared doesn't combine with anything else, so 6x squared. This diagonal shows me that I'm going to combine these two terms. 12 minus 14 is going to give me a negative 2x. And the last diagonal is this minus 28. And so what you may notice is that, let's say I have a 3x squared minus 7. Our diagonals might not be perfect, but the general idea is that we know we've combined everything with everything else in a two-dimensional fashion as opposed to a one-dimensional fashion here, and a kind of semi-two-dimensional fashion over here. But either way you work it, you're going to get the same answer. And the proper way that we're going to list our answers is what we call highest order or alphanumeric. What this means is that the alpha, let's do this in a purple color. So 1, alpha means alphabetical. Meaning we're going to list our terms from A to Z. We notice all three of these only had X's, so alphabetical really isn't too important. What we did need to do is we noticed we had the X squared first, then the X, and then the one without X. This comes from the second part, numeric, which means highest to lowest power. So that means my highest power is x2, x1, and this is technically an x to the 0th power because it has no power. And so let's do a few other examples on these three. So I tend to prefer the stacking method, simply because, like I said, it keeps things a little cleaner as we walk our way through. So as we work this out, I'm going to show the stacking method. We're going to distribute our first term. So x times x is going to give us an x squared. X times 30 is going to give us a 30x. Then as we distribute the second term, we get a minus 40x. 40 times 30 is going to give us a negative 1200. Again, the stacking method is nice and neat, where we know what columns we need to add up. So we get an x squared minus 10x minus 1200. Boom. And we're done. If we had something a little more complicated, let's say something with a coefficient in the front, it works exactly the same. If I were to say, hey, let's distribute this 2y times the 5y, we'll get a 10y squared. 2y times the 11 is going to give us a 22y. As we keep walking, negative 3 times 5y is going to give us a negative 15y. Negative 3 times 11 is negative 33. Again, we notice that as we go, we stack them according to where we see them. I saw I had another y term, so I stacked it right beneath there. And then we simply add them up. 10y squared plus 7y minus 33. Boom. There we go. The last one down here, this is not a binomial times a binomial, this is a binomial times a trinomial. And the benefit to this one is, again, this foiling does not work. We can't first, outer, inner, last because I have a middle term. If we did first, outer, inner, last, we'll notice that we missed that 5x completely. So we're going to have to use one of the other methods, which is, again, why I tend to like the stacking method. I'm going to multiply z times each one of these. So we'll get a 2z cubed, a 5z squared, and a minus 13z. When we do the same thing to the 14, I'm just going to search for those exponents specifically. 14 times 2 is 28z squared. So I'm going to keep it beneath my other z squared. 14 times 5, that would make a 70z. I'm going to stack it beneath my other z term. And then 14 times 13, well, let's see, 14 times 10 is going to be 140. 14 times 3, let's see, that would be 2 would be 28, plus another 14, that would be 32, 42. So 140 and 42 make 182. And lo and behold, this is nice and easy to set up. We have all of our columns stacked and ready to go. 2z cubed, 33z squared, positive 57z minus 182. Perfect. So this topic is arithmetic factoring. Again, this is another review subject. It's going to be composed of breaking down any composite number, which is made of two or more numbers multiplied together, into the numbers that made it up. So a number, for example, like 360 is 36 times 10. We're going to break down the 10 into 2 times 5, the 36 into 6 by 6. In each 6 breaks down into 2 and a 3. These bottom numbers are their prime factors. Now, the fun part about this is no matter how you break down that 360, you'll get to the same set of answers. 1, 2, 3 2s, 2 3s, and a 5, no matter how you break it down. So let's take a look and see what a set of numbers would look like. We're going to take 6 and say, what two numbers multiply to give me 6? Well, that would be a 2 and a 3, both of which are prime. So this prime factored would be a 2 times 3, just like that. 8, well, I could break that down into either a 2 and a 4 or a 2 and a 2, or a 4 and a 2, I should say. The 2 is prime, the 4 is not, so I'm going to break down the 4 one more time. Boom. There we go. We have 2's that are all prime. I can't break those down any further, so this factored is 2 to the third power. Now, you can break down bigger numbers like this, like 88, several different ways. One of the ways that I best see is if you can't recognize what I can break a number into, start checking from the smallest numbers possible. Can I divide it by 2? If it's even, yes. So let me go ahead and divide it by 2. That's 2 and 44. 2 is prime, 44 is not. I don't know what to divide it by, so I'm going to start at the lowest number. Is it even? Then the answer is yes, divide it by 2. Is it even? Then the answer is yes, divide it by 2. 11, let's see, I can't divide it by 2. 1 and 1 make 2, so I can't divide that by 3 because the digits don't add up. 4 doesn't work because that's a composite number. 5 because it doesn't end in a 5 or 0. 6, 7 doesn't work. 8, 9, 10. And then 11 is the next prime. So here we have 2 cubed times 11. So what I want you to do is I want you to break up 882, pause the video, break it down into its constituent parts, and resume the video when you're done. See how well you did. And keep in mind that we might break it down in a different way, but as long as you get the same prime factors, everything works out good. There's many ways to solve this, but as long as you get the same prime factors, you should be good. So go ahead and take a swing at it. Okay. So again, I don't know what to do, so I see that it's even. Let's break it down to 2 and 441. 2 is prime. Here it's not even, so I can't break it into 2, but 4 plus 4 plus 1 is 9. 9 is divisible by 3, so I'm going to divide that by 3. Let's see, 3 fits into 4 once, 1 left over. 3 fits into 14 4 times with 2 left over. And 3 fits into 21 7 times. Again, this isn't even, so I can't divide by 2, but 1 plus 4 is 5. 5 plus 7 is 12. 12 is divisible by 3, so therefore the whole thing is divisible by 3. 3 fits into 14 4 times with 2 left over. 3 fits into 27 9 times. And then 49 breaks down into 7 and 7. So our answer here is 2 times 3 squared times 7 squared. Perfect. Now, another way that you can factor is what we call the rainbow method. The rainbow method is going to be a little more useful when we're factoring, not because you'll actually need to make a rainbow. That's just where the name comes from, and we'll show you why, but because it lists all possible sets of composite factors. So the way that we build a rainbow is we say, Can I divide my number by 1? And I'll put that on the extreme left. Yes, 88 divided by 1 is 88. And we'll work our way up. Can I divide it by 2? Yes, that'd be 2 and 44. Can I divide it by 3? Well, no, because 8 and 8 make 16, which is not divisible by 3. Can I divide it by 4? The answer is yes, 4 and 22. 5 doesn't work, 6 doesn't work, 7 doesn't work, 8 works because it's 8 times 11, 9 doesn't work, 10 doesn't work, and 11 does, but we've reached the other side of the rainbow. So at this point, we've done what we've called completing the loop. Once we've made it through this middle section, we don't need to try anything else because we know where the next tries are. And the rainbow method comes from this pretty connection that we show which factors connected. Boom. And there's our rainbow method. Now, again, the fun part about the rainbow method is you're really not going to be making rainbows too much, but you're going to be making each of these pairs of composite numbers in a list. So we would have a list like 1 and 88, 2 and 44, 4 and 22, 8 and 11 would be in a list that we're going to be building for something later on. So I want you to try 180, break it down, see how big your rainbow is, and go ahead and be prepared to write a little small, but give it a shot. Unpause it when you're done and see how well you did. Okay, so let's see. I can divide 180 by 1 for 180. I can divide it by 2 for 90. I can divide it by 3 and 60. 4 and 45. Let's see, 5 and 36. 7. See that? Nope, 7 doesn't work. 8. Let's see, 8 fits in. Nope. 9, yes. 10. 11. And let's see, 12 fits in 120 plus 60. So 12 and 1, 5, 15 times. And then between 12 and 15, 13, 14 don't work, so we've completed the loop. Or in essence, what we've done is we have completed the rainbow. So 12 and 15, 10 and 18, 20 and 9, 36 and 5, 45 and 4, 60 and 3, 90 and 2, and then 180 and 1, and boom, we've completed our rainbow. Now again, we're not so much concerned about making a rainbow when we factor these things, but we will make a list of like 1 and 180, 2 and 90, 3 and 60, all the way down until we get to 12 and 15. And these are the lists in a table that we're going to be using in a later section. There we go. Okay, so this topic, we're going to be factoring out the GCF. And so you might ask yourself, well, what is a GCF? Well, a GCF stands for the greatest common factor. And this means that we're going to pick the biggest thing that everything shares that we can factor out. So what is the biggest number that we can divide out of everything? Which is exactly where our definition comes from. This means we have to factor out each term and find what factors are shared by all terms. So let's go ahead and let's fill out this. This isn't a true proof, but it's a general proof idea so that when you cover a geometry class, you're going to be setting up proofs just like this. So a proof is we do the steps on the left and we do the reasonings on the right. These aren't tried and true mathematical definitions. This is more a step-by-step box, but that is literally all the geometry proofs consist of. let's go ahead and take a look at it. We're given this expression, 5x cubed plus 25x squared plus 45x, and we want to factor that. Okay, perfect. Well, we're going to factor down each term into its prime factors. So our first step is to take each one of these numbers, 5, 25, and 45, and break them down. 5 can't be broken down at all, so we're going to leave that as a 5. X, however, can. X, x, x. 3 x's make x cubed. Next, I'm going to add whatever my factors are for 25. So I'm going to come over here and build a factor tree for 25. There's only 2 factors of 25, and it's going to be 5 and 5. So what we're going to do is we're going to add a 5 times 5 times x for the x squared. So 25x squared is the same thing as saying 5 times 5 times x times x. And we're going to add in the last term. Now, the 45, let's see, we have our 45. We're going to break that down into a 9 and a 5, 5 being prime. The 9 we can break down a little further into a set of 3s. So what we're going to do is we're going to list that as 3 times 3 times 5 times x. Perfect. So we broke down the term into its prime factors. Next, what we're going to do is we're going to identify and circle all the terms that they share. Well, let's take a quick look. I have term 1, term 2, and term 3. So when I say identify all the terms that they share, what I'm really saying is all the prime factors that they share. So we notice that each one of these shares a 5 as part of it. So I know I'm sharing at least that number. Next, we notice that each one of them shares an x. So I can plot an x as well. Step 3 is write what's inside those circles outside a set of parentheses. So 5x, I'm going to write that right there, and outside a set of parentheses. And I'm going to write what wasn't circled inside them. So I didn't circle 2 x's. I didn't circle a 5 and an x. I didn't circle a 3 and a 3. Perfect. And the last step is simplify the inside and the outside separately. A common mistake that students do is they go and they redistribute this 5x back into there, forgetting the fact that our whole point was to get it out. So make sure we simplify the outside and the inside in 2 separate pieces. 5x can't be simplified. However, x times x can. X times x is just x squared. This is going to be a 5x. Nothing else can be simplified. Our 3 by 3 can be simplified into a 9. And boom, we factored out a GCF. Now, typically, we're not going to break it down like this every single time. But we've shown the fact that this is what it means to pull out a common factor. We literally pull out a 5 out of each one, pull an x out of each one, and then we simplify what's left over. Most of the time, what you're going to see is you're going to see something like this. It's going to be shown as 5x cubed plus 25x squared plus 45x. And you're going to see somebody write a giant division sign and say, I can divide each one of these by 5 and by x, which is going to lead them to saying, okay, that means 5x is on the outside. They'll take each one of these terms. 5 divided by 5 is 1. 25 divided by 5 is 5. 45 divided by 5 is 9. And then we get rid of the x's. 3 x's divide out 1. 2. 2 x's divide out 1. 1. 1 x divide out 1. Nothing. And you'll get something that looks like this. This is typically the way it's shown, but this is explaining where that answer comes from. We're dividing out the biggest thing we can by doing this process. So the last step is you could actually distribute, if you want to check your work, you could distribute that back in to see if you get the original problem. So the way to check that would be we would just say 5x times x x squared plus 9, and we would distribute this in. So 5x times x squared is 5x cubed. 5x times 5x is 25x squared. 5x times 9 is 45x. We check that against our original question. They match up, which means yes, this is the correct factored form. So let's try a few examples. Now, the first one, what we have is we have simply a numeric factor. I notice an x, a y, and a z, so they don't share anything in common. But I do notice that each one of them can be divided by the number 5. So what I'm going to do is I'm going to put 5 outside a set of parentheses, and I'm going to divide each thing by 5. 5 divided by 5 is 1. 15 divided by 5 is 3. Negative 20 divided by 5 is negative 4. Then I go back and put the remaining variables in. Because I didn't remove any variables, they all stay in. And there we go. If you wanted something other than numeric, you could try a variable. I noticed that 2 and 3 are both prime numbers as well as 7, so I can't divide them by anything. But I do notice that they all have at least one x. Now you may be tempted to put a higher number, like a squared or a cubed, but remember, we're going with the lowest number possible because it's what they all share. They all share at least one x, even though these have more. The largest I can pull out of that last term is 1. Same thing right here. The largest I can pull out of this last term is a single x. So I can't pull any more than just that. I say, okay, so 2, negative 3, and 7 all stay the same because nothing was divided out numerically. But I knew that 3x's divide out 1 is going to leave me with an x squared. 2x divide away 1, that's going to leave me with a 1x. X divide away an x, that's going to leave me with nothing. Boom. There we go. And if you have a good idea on those, go ahead and pause the video, try number 7. It's got both, I guess you would say, the alpha and the numeric aspect of it. It has both the variable and the constants. Unpause it when you're done and see how well you did. Perfect. So what you may notice is that we're going to have to do 2 pieces like this. First, I'm going to look at the 3 numbers. The smallest number is 6, and lo and behold, I can divide all 3 numbers by 6, which means that the first part, I'm going to divide out my numbers. So 12 divided by 6 is 2. 6 divided by 6 is 1. 18 divided by 6 is 3. But that's not it. I also noticed, just like the prior one, they all share at least one x value. So not only am I going to divide out a 6, I'm also going to divide out an x. And what that means is that I'm going to get rid of the x terms as well. 3x's divide away 1, 2x's. 2 divide away 1, 1x. 1 divided by 1, no x's. And there we go. Okay, so this topic is going to be our first factoring topic, and it's going to be factoring by grouping. Now, factoring by grouping, presently, the way we're going to set this up is a good candidate is going to be 4 or more terms. So let's take a quick look at 4 or more terms and see which ones fit that criteria. Well, going through this list, we already see that these 2 don't have 4 terms, so they don't qualify. We notice that these have 4 terms. This has 4 terms, as well as this. And we might be tempted to look at this one as well. But one of the things that we want to notice is that I have an x squared and an x squared. What happens when we combine them? We get 3 terms, and that wouldn't work. Now, we will actually learn a way to take a 3 term, turn it into a 4 term, so we can do that later on. But for today, we're simply looking at polynomials that have 4 or more terms. So the last thing before we actually begin and show an example is that we're going to group these by a 2 and 2. So we're going to group first 2, last 2. We're going to factor out the GCF once and then do it again. However, a big thing is this doesn't always work the first time, because how many different groups can we make out of 4 terms? Well, let's take an example. Let's give 4 pens. Okay, so this is one possible combination. I have a group of 2 and 2. However, red might not work well with green. So what I might do is I might move green over here with orange and pair red up with purple. That's 2. But also, purple doesn't work well with red either. So I'm going to move purple over here, and I'm going to pair red up with orange. That's 3. Can't pair red up with anything else, so that's going to be it. So out of 4 possible terms, you may need to work these problems up to 3 times to find the answer. Now realize, in the beginning, we're going to set this up so that you only need to work it 1 time. It's ready for this. However, later on, you might need to rework it a couple different ways to figure out which pairing works, because not all the time does every pairing work. But let's take a look at one of the ones that we're going to be doing something like here in just a minute. Now, this is the full-on skill. So if we can understand this first one, we don't need to actually go through any of the examples. But let's take a shot and look at this. Now, we're going to be breaking this up into 2 different pieces. We're going to break it up into the left 2 and into the right 2. So if we were to take the left 2 and simply look at them, do we see any sort of GCF? Any sort of common factor between a 2, an x squared, and then with an a and a y? Well, the answer is no, there's nothing in common. If I look at the other side, there's nothing in common other than maybe the fact they have a negative sign. So we're going to need to repair these. So I'm going to take this one, and I'm going to look to see, do I see either an x squared, or a 2 anywhere else? And boom, I have 2 possible combinations here. I can either pair this x squared up with this x squared, or this 2 up with this 2. So we're going to start by pairing up the variables first, simply because that's going to be your best bet later on. However, you might need to look a little deeper and pull out some common factors. Even if it's not a 2 and a 2, you might have a 4 and a 2. But again, we're going with this here. So I'm going to pair these up, and I'm going to pair these up separately. So I'm going to rewrite this as a 2x squared minus ax squared. And then I'm going to write my ay minus 2y. Perfect. And so just like what we've done prior, I'm going to look at only the left-hand part of this polynomial. And I'm going to say, okay, what is the GCF here? What can I divide both this and this by? Well, the reason why we put them together is because they both share an x squared, which means I'm going to put this x squared outside a set of parentheses. X squared take away x squared is going to leave me with a 2. Negative ax squared take away the x squared is going to leave me with an a. Boom. And there we go. So we factored out the GCF. Now we do it again. And we say, okay, looking at only these 2 terms, what is the common factor over here? Well, I have an ay and a negative 2y. Well, that would be my y. So I'm going to write my y outside a set of parentheses, and I'm going to take away the y out of both of them. This leaves me with an a and a 2. Now that y, for the second time, whenever we do it to the right half, that's a positive y. So we're going to make sure that y shows the positive sign, because that keeps our whole expression equivalent. And the next thing we're going to notice, we're going to say, hey, I notice I have a 2 and an a in both of these inside the black parentheses. The only problem is this 2 is positive and that 2 is negative. This a is negative and that a is positive. So if only there were a way to swap the signs over here, that'd be perfect. And long story short, there is. What we can do is I can keep the x squared, I can keep the 2 minus a, but if I were to pull a negative outside of that and divide both of these by a negative 1, that would mean that my plus y would become a minus y. I factored out a negative 1. What that'll do is that'll change that a to a negative, so negative a, and that 2 to a positive. Boom. So now we can look at it like this. Then lo and behold, just like what we did here earlier where we were looking at what do they both share, what do they both share, now we're looking at these two terms right here and right here and saying, what do these two terms share? Well, they both share a 2 minus a. So just like what we did right here, and we divided them out, let's go ahead and put the 2 minus a off to the side. And what are we left with? An x squared minus y. Boom. And so again, this is a full example of everything we're about to do. So if you understand how to do this, awesome. You don't need to watch any further. But if this was a little confusing, or if you see that there is a pattern here, go ahead and check out a few of these examples. Let's see how to do it building from the ground up. So let's go ahead and jump full in. What we're seeing right here is we see the fact that we have a descending set of x's, x cubed, x squared, x, no x. This is going to be the best way to set up your groups if you want to have it grouped the right way the first time. Generally just set it up in alphanumeric order. So what we're going to do is, again, just like what we did earlier. I'm only going to look at the left half and say, what can I divide both of these by? Well, I can divide the numbers by 6, and they both share at least 2 x's. So I'm going to write a 6x squared outside a set of parentheses. 24 divided by 6 is 4. 6 divided by 6 is 1. Then I'm going to take away the x squared, so nothing left right here. Take away an x squared, which leaves me with 1x. So I have a 6x squared times 4x minus 1. And then we do it to the other side. And so this side, same process. What can I divide both numbers by? 2. So I'm going to put the 2 outside a set of parentheses, and because this is the second time I'm doing it, plus 2, and divide it out. 4x minus 1. Lo and behold, what I notice is that both terms have a 4x minus 1. So again, what we're going to do is divide this all by a 4x minus 1, which means that I can pull that out and say 4x minus 1, just like we did with our red. We divided it and moved it to the side. I'm going to divide it and move this to the side, which leaves me with a 6x squared plus 2 over here. And that is going to be where we stop for today. Some of you might say, well, hey, I can still factor out a 2 out of here, and then theoretically you could factor this a little further. But again, if we're just factoring by grouping, this is the concept that we're going to be teaching. How do I take a polynomial, turn it into a binomial? We're not worried about fully factoring it just yet. So number 3, same concept. We're going to factor the left side, which is going to be 4y cubed plus 2y squared. I notice I can divide them both by 2 and divide out y squared out of both of them, which leaves me with 2y squared. Inside, 4 divided by 2 is 2. 3 y's divide out 2 is leaving me with a y. 2 divided by 2 is 1. Y squared divided by y squared, no y's left. So we're done. On this side, what we notice is that I can't divide 2 and 1 by anything. So it looks like I'm just going to pull out a 1. But a trick here, and let's go ahead and write this, is if the leading coefficient is negative, divide out a negative GCF. So a trick here is that we notice that when we're done, we had a positive leading coefficient here. So no matter what we divide out, if I don't get rid of that negative, my leading coefficient will be negative as well. So a general rule is that if I ever see a negative, just make whatever we're about to divide out also negative. So -1. And then basically all I have to do right here is change the signs. 2y plus 1. I notice they both share that, so I'm going to divide out a 2y plus 1, which gives me an answer of 2y plus 1, 2y squared minus 1. Boom. And there we go. So if you need a few more examples, we get a few more over here. Again, if at any point you kind of understand this, this is just review building our way up from the ground. So at this point, I'm not going to cover up the left and the right-hand side. We're going to look at the left-hand side and say, hey, what can I divide those two numbers by? Well, 4y squared. So if I leave that 4y squared over here, I'm going to have a 1y plus 2. Awesome. Over here, I'm going to do the same thing. I'm going to divide that out by a 3. So positive 3. That's going to leave me with a 1y plus 2. Again, right here, I can divide out the 1y plus 2, which leaves me with, I actually don't need to write the 1. That's an understood thing. So y plus 2, and then we'll have a 4y squared plus 3. And there's our answer. If you need another one, look at the left-hand side. These are a little bigger. So what can I divide 66 and 36 by? Well, 66 is 6 by 11. 36 is 6 by 6. So I can divide them both by 6, along with an x squared. Over here, 55 and 30, that's 5 by 11. This is 5 by 6. So I can divide them both by 5. So I'm going to move my 6x squared on the outside, leave a set of parentheses, and do the same to my 5, and leave a set of parentheses. That's going to leave me with an 11x minus 6. This is also going to leave me with 11x minus 6. And because these are the same thing, I'm going to divide out that 11x minus 6 to leave me with a 6x squared plus 5. Awesome. Okay, and so the next one, I want you to give a shot at the next one and see if you can identify where the issue might be compared to what we've talked about so far. Okay, so what you might notice is that unlike prior, I'm no longer in descending order. I'm no longer in alphanumeric. I have a z cubed. The z squared is all the way at the end. The z is third in line. My constant is way up here at the front. So if we want to group this, our best bet is to go ahead and put this in alphanumeric order. So I'm going to rewrite this as 3z cubed minus 9z squared plus 2z minus 6. Descending powers is what we call alphanumeric order. And this allows us to, when we group, get the best chance for pairings possible. Here we'll have a 3z squared, and over here we'll have a 2. So 3z squared plus 2. Let's see, that's going to leave me with a z minus 3. Here we'll have the same thing, z minus 3. So when I divide out the z minus 3, what we're left with is a z minus 3 and a 3z squared plus 2. Awesome. So after you've seen that, go ahead and try the next one. Try number 11 and see how well you do. Perfect. So what a lot of you may have noticed is that this is not in alphanumeric order. First off, we want to list this in alphabetical order. So I have a y, W, X, and another X. So my first step is say, okay, these X's need to go first. So X, let's see, Y, W, X, Y, Z. So W is going to come first. So I have an XW. It's a really awkward W. Then I'll have my negative XY squared. This is not an alphanumeric order. The W comes first out of everything, but for some reason I went with the X first. So we're going to ignore that and act like it's okay. It's going to end up working out because we have the X's paired up together. Next, let's just go ahead. We had the W first and the Y squared second. So let's the W term first, so negative 5W, and the Y squared term second, so plus 5Y squared. A little awkward, but I think it worked out okay. We're going to take a look and say, well, I paired up the X's, so I know it's going to be an X. Over here, remember I have my leading coefficient is negative, so I'm going to pull out a negative, and I can divide them both by 5. So X and minus 5. Take away the X, I'm left with the W minus Y squared. Divide by negative 5, I'm left with the W. Divide by negative 5, that's going to be a negative Y squared. Lo and behold, because they both have a W minus Y squared, what we're left with is a W minus Y squared as my first term, and then an X minus 5 as my second term. Boom. There we go. And so the last one, this was our example at the beginning, so we're going to kind of gloss over that one because this has already been proven. But at the very, very bottom, what I want you to try is this is a challenge. Try using the same technique we just used on a polynomial with 4 or more terms and ask yourself, does this process work? Notice they're both in alphanumeric order, so give it a shot on both of these and see what answer you come up with. Okay. So at this point, you should have tried. And what we notice is that if I pair them up, and I pair them up into groups of 2, let's see, I can divide them both by 2x4. I can divide these by a 3x squared. And I can divide these by a negative, because that leading negative coefficient, 7. What that leaves me with is a 2x4 plus 3x squared minus 7. It's going to leave me with a 1x, so x minus 3. That's going to leave me with a single x minus 3. And this is going to leave me with a single x minus 3. So lo and behold, this can actually work. If I divide this all by an x minus 3, I get x minus 3, parentheses, 2x4 plus 3x2 minus 7. And so yes, this works. But what you might have noticed is that when we try this one, and we group them, that's x to the 4th. 7 and 22 don't share anything other than x squared. Let's see, 24 is 3 by 8. This is 5 by 11, so nothing. So x to the 4th plus x squared plus 1. That leaves you with an x plus 3. Ooh, the leading coefficient is negative, so I'm going to make that a minus x squared. That's going to leave me with a 7x minus 22. That's going to leave me with a 24x minus 55. And what we notice is that these are not the same thing, so I cannot factor this way. And if I group them up differently, I would still run into the same problem. So if I cannot factor this, no, this does not always work. And we'll have to learn different ways to solve these questions. There we go.